So, welcome to my dear students. So, this is a very introductory session to use COMSOL multiphysics for aerodynamics. Uh, Basically, right now I'll show you the how the COMSOL multiphysics can be used for airfoil simulation. Okay, there are a lot of things could be done, but this small introductory session is basically for to create the interest for the one of my new students. He will be hereafter working with me for this aerodynamic stability and simulation. So to start with that, just I want to show the how COMSOL multiphysics can be used. So we'll be using one particular for this lecture. I will use NACA 0012 airfoil. So this is a particular airfoil designed by NACA, that means National Advisory Committee for Aeronautics. Later on now it is NASA. Before took over by NASA, the name was National Advisory Committee for Aeronautics. So this is the geometry of the airfoil, and you can see the chord length is exactly 1 meter, and this 00, the first two digit, uh, the the indexing is like that. The first two digit, it is this 00 means it's a symmetric airfoil without chamber, and the 12, the second, the third and fourth digit, it will indicate the thickness of the foil. Basically it is 12% of the chord length. So that means if you see here, the maximum thickness, it will be around 12% of 1000 means 1 meter, around 120. Okay, so we'll in the software, in the COMSOL multiphysics. So this is the software basically what we'll be using. It will take some time because those are the, so you can go to the model wizard and we'll do the 2D study. Slowly we will do for 3D study also. So there you have to use some CAD modeling software like SolidWorks, and from there you have to make the geometry and convert that geometry to STL or IGS file. Then that same file can be imported here and apply the boundary condition and then the simulation. Okay, so this is related to airflow. So we'll be going to fluid flow, and then it is a single phase flow. Then in the aircraft, this will be moving very fast speed, very high speed. So this will be, the Reynolds number will be very high in the flow, airflow. So we'll be using, better to use turbulent flow. So there are a lot of models are there. So here we are going to use this. Okay, I will explain one by one where what module could be used and what is here, all these things. Then we'll go for the study, and today we will go for this particular session lecture. We will go for the steady state analysis, because you know that transient analysis will take a lot of time and memory. So basically this is the interface. Okay, now to make the geometry, that particular airfoil, we'll slightly modify the geometry. Okay, in the airfoil NACA 0012, will that flap will slightly will incline some 15 degree, and we'll see, we'll simulate that velocity and pressure distribution, and slowly the next lecture we will calculate the lift and drag. Okay, lift and drag coefficient. From that we can uh, estimate, we can have an idea that this will be lifting. Okay, so for that, actually, to generate that particular geometry, we'll use one ready-made portal that is from MIT. If you open that link, this is the link. This is, there is a airfoil here. You download this, simply download and unzip it. If you download and unzip these things, it will come, and click here. This is the interface, it will come. Then here you give a command naka 0012. So these are the details. You can see this is the details, and if you see the things, this is the airfoil exactly which you have seen, correct? It's exactly the things which you have seen. Then okay, so we want to give, sorry, naka 0012, and then we'll gdes. This is the thing, and here this has come. Okay, so now we'll give a command, because as I told, we are going to modify slightly. Okay, so let us the hinge where the flap will be, there will be some geometry, change of geometry. So here we will give that is a point arbitrary, you can give 0.7. Then enter the flap hinge y location. Y, it will be in the 0th position only, in the along the symmetry. So that's why I'm giving 0. Then the flap deflection will give, say it is a 15 degree. Now you see, now the new geometry, and you can see it here. See that it is slightly, so from this location, uh, uh, you can this is the 0.7, you can see this is the 0.7, and the y location is I given 0, and this degree, this angle, it is a 15-degree angle. Okay, so that we have done. Then we have to save it, basically, that data. So for that, this is the command. So now it is in that particular, now the new geometry is, we are considering the new geometry, and we will give a command to save it. So this is the command to save it. So now you give the file name, that is naka 0012 underscore modified or something you give. Then that is saved. You can see here, you see that file has been saved. It's basically giving the x and y geometry. Once you import the file, you can see what is this basically. Open with, if you see notepad, you see this is the xy geometry. It will otherwise, if you want to do it manually, it will take more time. So this particular software is very helpful to import the geometry. Now I'm going to the console, and here in the geometry tab, or here in the geometry, if you see, there are the primitives, and here something we can go for mm, we can go for polygon, and here we can go for a file and we can browse it. That basically it will be D drive downloads, then X file, and all file. This file, if you open and build selected, you see that particular geometry is created. Okay, the exactly whatever you have seen, this has been imported here. Okay, now I will give a for a air, this air volume. Will for that we will go for the rectangle, and that width we will give some, say, uh, 1.5 meter, and this height will give, say, 1.2 meter, and it is 0. 1.2 means, so the corner, the x corner will be here somewhere. We will give somewhere here. So 0.61%. So we'll give some, x corner is minus 300 mm, and y corner will give so 300 means this side it will go, and y corner will give 6. Okay, minus 0.600, and build selected. See where it is. So it is like this something. Okay, now we have to consider this area only air, and this will be empty, and here the inlet, this is the inlet, and that will be the outlet. So air will pass through. You can consider this rectangle as a air tunnel. So here the air will be flowing and coming out through this, and for that particular case we are going to check the velocity distribution along the line, the airfoil uh, periphery. Okay, so for that we'll go for the boolean operation and we'll go for the difference. So here the main objective, the object will be this one, and we will want to subtract that particular airfoil, and if we build selected, you see that area is subtracted. Okay, now we have to give the material. You right click on the material, add from library. You can go for, my eyesight is not good, so here built in we go, and we'll select there. So automatically all the parameters which will be needed for the study, it has come along with the material. Now we will go for the inlet. So we have to define the inlet. So let us define the inlet, and the velocity you take, say, 50 meter per second, and simply the outlet. So you define the outlet which is open to atmosphere like this. Then we'll go for the mesh. Here for meshing I will take separate session. Is very important to converge the solution, and for quick solution, accurate solution. So we'll go for the finer. So let us see how it is. So it will take more time. So we'll take fine. Now you see the degree of freedom. So this consists of 25,000. If you increase, then these all values will be increasing, and your solution accuracy will be much more better. Now if you go for the study, and if you click the compute, it will take some time. So normally I will suggest my students who are going to do much more with the simulation and all. So definitely their RAM, at least the RAM will be 32 GB minimum, or 64 GB, even though 128 GB will be much more better. And as it will be related with graphics. So definitely in your computer or laptop should have some graphics card, nvidia graphics card of at least 32 16 GB or 32 GB. That will be better, then you can achieve the quick solution. The people who are already working in R&D organizations or universities, so definitely those people have a workstation, higher capacity, the workstation with better computational capability or the clustering. So there it will be much more faster. So this is taking some time, and the file, you can see the file is around 2 GB. So that's why it is taking some time. It will take some time. I don't know finally it will give the solution or not, because my hard disk capacity also, you see, it is solved for 76,040 degree of freedom. That means that many differential equation it solved. Okay, and we will finally will give the solution. So it is taking some time. So let us pause for a moment. So as I was telling, my memory was too low. In the mesh, if you see in the mesh, I have done very a coarse type of mesh to reduce the degree of freedom. Now, anyway, you can see for that this kind of application, you need very high capacity. The memory should be very high. So now you can see in the what we are going to basically understand. So here you see in the upper side of the foil, the velocity is very high, and the below is in the, you see, in the top side it will be in the range of 70 meter per second, and whereas in the downside it will be lesser than 50, or within I think it will be within 40 to 50. So now, as per the Barnell's equation, in if the velocity is high, the pressure is low, and the lower velocity is the pressure is high. So definitely there will be lift. So that lift and drag, all these things, it will learn in the next lecture, which need the line integral. So you have to integrate over uh, this periphery, then we will get it. So basically this way, this COMSOL, it will be used for can be used in effectively we can use in aerodynamics. Okay, so thank you so much. Thanks for your patience. We'll meet again.